The t-test for independent groups is probably the most common statistic you're going to encounter. It's a simple experiment where it only has two levels of the independent variable. It has a nice continuous dependent variable. It's classic control and experimental condition when you have between subjects design. It is far and away the most common stat to use. So this again is if you have two samples, not a population anymore, just one sample compared to another sample. It's independent sample t-test, sometimes called t-test for independent groups, slightly different names, they all mean the same thing. Here's the formula. The numerator is just the difference between the two means, the mean of the first group minus the mean of the second group. And the denominator, this is something called this, it's still the standard error. The book tries to use this little nomenclature, standard error, the difference, to separate it out from the first standard error we're talking about. And this is the formula for standard error of the difference in this problem. Don't let this confuse you. This isn't too fancy. This is just the standard error, remember, S over the square root of n, and then we're going to square all that for the first group and do the same thing for the second group. But this is confusing. This really messes up students. But if you can just take this standard error, turn it into this, S over the square root of n. So this is just S for the first group, n for the first group, and then we're going to square it. That equals one of these. And then you do the same thing for the second group. Add them together, take the square root of them. The degrees of freedom for this is a little different. Sample size of one sample minus 1 plus the sample size of the second sample minus 1. So if we do the calculation, we're doing this experiment on a cancer drug. We have a group that doesn't get the drug. We have a group that does get the drug. We have mean differences and standard deviations. We calculate the differences. We plug in the values. The numerator is always the easiest to calculate. The denominator is always tricky. But if you just convert these into S over the square root of n, S over the square root of n, S over the square root of n, it simplifies the entire equation. We come up with a t of 18.71. Then we go to the t-table to determine if we're significant. Our degrees of freedom, 50 minus 1 plus 50 minus 1 equals 98. We know it's a one-tailed test because the hypothesis said Herceptin was trying to reduce breast cancer. That's directional. And at 0.05, we go to the z-table at 90 degrees of freedom of 98, and we see that our stat is 1.671. That's our critical t. Since our t that we calculated is larger than that, we say that our statistic is significant and Herceptin does indeed reduce breast cancer. Let's go to the z-table to see that. The t-table to see that. There's a little bit something a little different here. One-tailed test, 0.05, we're going to use this column. But our degrees of freedom was 98. You notice there is no 98 in the file here. So what you do in that case is just round down to the nearest one. We'll use 60 instead, and we'll use 1.671 as our critical t. And still, our t-test was highly significant with a t of 18.71. So that's how you calculate the most common t-test that is used by behavioral scientists. T-test for independent groups or independent samples.